Right. So yeah. So like federated learning is a relatively new concept in A and ML, where the model is sent to the nodes instead of like centrally aggregating data. So like traditionally we have been aggregating data, and centralized data is what was used for training. And the AML is notorious for like requiring large number of data. But like a lot of situations that cannot happen, and that is where federated learning comes in, and that sets the context of our work. So yeah, so the agenda for my presentation today will be that I'll start with the motivation, overall motivation for federated learning, and given overview of what an federated learning flow looks like. This is to just set the context and understand the terminologies that will flow after that, and talk about some of the challenges, and how our algorithm, which is called divide and conquer algorithm, addresses some of those, and conclude with results and summary from our work. So starting with motivation. So I think data is the new oil, and that is something that people would have heard quite often these days. So though like we deal with the data sets like MNIST and CFAR and ImageNet, most of the time for real world use cases, like the data that are from critical applications will not be shared across organizations. So like that puts an limit on how much data you can have, and challenge that also sets the challenge in scenarios like maybe an brain tumor detection, or some financial fraud detection kind of cases. In addition to the business criticality of the data, there are also like a lot of regulations like GDPR, which impair centralized collections. And yeah, there is also this increasing compute that is available at head, that kind of starts favoring and distributed or disaggregated kind of data learning. So like yeah, what federated learning would allow is to like help people move away from CFAR 10 and MNIST kind of data sets, and start really focusing on the ones that matter in areas like healthcare and finance and so on and so forth. And the conceptual flow of federated learning looks something like this, where data will reside at individual collaborators or nodes that are kind of separated. In case of an situation like an healthcare data model, like an tumor kind of data model, this could be the imaging data that resides at different hospitals. So multiple hospitals collaborate to develop a common model, but yeah, each has a limited set of data that sits within it. And there is a central aggregator that kind of takes this model and orchestrates the overall training process. And for training itself, the model is sent to these collaborators, and they learn on the data that reside at the collaborator. So that helps with privacy and other concerns. And once model is learned, the model is sent back to aggregator, and the different versions of the model are kind of aggregated together, and we end up with a single global model. And this process is repeated multiple times, because with single iteration you end up with a case where each model will kind of fit to the bias or local data, or kind of overfit to the local data, and may not generalize as well. So like the setup is repeated multiple times, and as a result of that, this process is kind of compute heavy, and especially on the edge nodes, and also bandwidth heavy, because the model has to be transferred back and forth for each communication round. um, so yeah, I think with that, to list some of the challenges, like each uh, collaborator or a participating node may have its own version of data. Like the data is not going to be uniform and identically distributed. This presents bias in the data, and often lead to overfitting when a model is solely focused on few collaborators. And the data heterogeneity can come from multiple things like demographics and other scenarios. And yeah, like since the training happens on the edge, like there are also like compute and memory requirements that this challenges that this methodology imposes, in addition to high bandwidth requirements, because like for each communication round the model has to be sent twice, once from the aggregator to all the collaborators, and once again back from the collaborator to the aggregator. And large scale federation was initially like proposed by Google, where they tried to learn the keyboard next character prediction and word prediction. So like when we type something in our cell phone keyboards, it does an autocomplete, and the model is actually like learned using federated techniques. So like for such a large scale training, then I think like you'll have thousands of collaborators, and the data transmission and the bandwidth associated with it becomes a serious problem. There are several techniques currently addressing this issue. There are techniques like federated average. This is from Google again, and where the model from different collaborators are taken, and for each weight, like there is an averaging happening, and the averaging is done using weighted average. So like depending on the number of data that each collaborator has, you just do an weighted sum of the weights from the collaborator. There are also like a little better techniques like FedProx, where some kind of regularization is applied, and the regularization specifically aims to minimize the weight divergence. So the idea behind this is like when you have data diversity, like when you have different kind of data in different collaborators, uh, each model will kind of try to move in its own direction to fit the data, and as a result your weights will start diverging across the different collaborators, and when that happens, you will have trouble coming up with a final aggregated global model. So here by forcing and regularization term, which is the difference between the starting weights for a round and the weight during the training, uh, this particular algorithm kind of makes sure that the weights between the different collaborators kind of are constrained, and in doing so helps with the better convergence and good accuracy. And there are also like more fancier algorithms like FedMA. MA stands for matched averaging, which look at individual layers and individual kernels in the layers, and see like which kernel kind of aligns, and like and based on that do an averaging. So the challenge they proposed is something like this, where if you have two different models in two different collaborators, there can be this permutation invariance, wherein one due to stochastic gradient descent, like it's which is non-deterministic, like you can run into case where like the first model, even though they learn the same things, the position of the kernels may be swapped. So in the first example, like we have an horizontal detector as the first kernel, and on the second collaborator, like the positions are swapped. So like in case of this permutation invariance issue that can occur in case of distributed learning, we will end up with a case that simple averaging of these models will often result in incorrect models. Though this will be corrected over time when the different models are kind of aggregated multiple times, this severely impairs the overall training time. And they propose that like we will do an alignment of these kernels first by looking at the kernels, and then do an averaging. But practically we have seen that like methods like this are like take a lot of time, and like as the model increases in depth and width, doesn't really scale well. Our approach is mostly along the lines of FedAvg, and this is an algorithm that is present in a lot of federated learning frameworks, starting from TensorFlow, federated PyShift, and Intel's own OpenFL algorithms. So our focus was mostly to try to leverage our Fed averaging, and still identify opportunities for so the algorithm that we came up with is called divide and conquer. It's more of an optimization training methodology than an algorithm itself. But yeah, the benefit of the algorithm is mostly that it's simple and gives very good results. So yeah, let's On the algorithm itself, this kind of leverages the common knowledge that within a deep learning network, the initial layers are mostly class agnostic, or the initial layers of the network try to learn the class agnostic kind of features or low level features, where while the later layers of the network mostly focus on class specific layers, class specific knowledge. So we attempt to like break the network into two components, class agnostic and class specific layers, and train each of those two components separately in separate rounds. And as a result, like we have the advantage or flexibility of training each component in a different way. So like even the hyperparameters like number of epochs and learning rate will be different for the class agnostic layers and class specific layers. And the novelty that we have is the methodology to split the topology itself. Like given a deep neural network, how do you split it into two components? And for that, we use weight divergence itself again. So what I'm showing here is a couple of examples on different possible splits for this particular topology. This is an VGG9 topology. So on the right bottom, I mean right top, I have VGG9 divide 3, where we have divided the network into two pieces, and the first three layers are grouped under the class agnostic layers, and the remaining layers are grouped under class specific layers. And for our methodology, we would train the class specific layers less aggressively, and more like a traditional fine tuning type method. And the class specific class agnostic layers will be trained like feature learning. So the combination of feature learning and fine tuning would help us achieve good accuracy. And how we split itself is based on weight divergence, and that I will cover in the next step. So the core idea of the algorithm is to split and model into two pieces and train each piece with its own set of hyperparameters. So yeah, this plot here shows the impact on the model accuracy as we do this uh, 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 feature learning and fine tuning kind of alternate training methodology. So like what I have is results of the convergence profile of the model as we split the model at different places. So like this thing shows divide 4 through divide 8, where the model is split at that particular layer number, and the corresponding accuracy that is seen with the model. So like when for instance, if divide 7 is used, which is the plot with the yellow line, we find that the a zigzag plot where it dips for feature learning and goes up for fine tuning. And if you just look at divide 4, it just shows the opposite behavior, wherein like your accuracy is higher for the fine tuning, and it dips for the feature learning. So it gives an indication that the model is over parameterized, or the for some splits in the fine tuning area, or it's kind of over parameterized for the feature learning kind of group. And with divergence, we aim to come up with an optimal split. And at least from a figure, like we can see that the divide 5 more or less looks like an optimal split for this particular topology and the given data set. And I think we also show that using weight divergence, we achieve similar results. I think before I go into the results, I think I will talk about the simulation setup that we have. So again, currently this experiments were run using CIFAR 10, which is a public data set, and also a data set called Shakespeare data set, which does a next character prediction. And for these data sets, these are central data sets. We just take them and do data sharding so that we simulate for this non-IIDness or data heterogeneity. So we take this and make sure that when we assign it to a set of collaborators, we do a non-uniform kind of assignment, and doing so we simulate for heterogeneity. And yeah, and we simulated the CIFAR-10 under two different kind of setups. One is what is called color imbalance, where we just took the 50,000 images from the dataset and split it into two groups, 25K each. And for one group, we made sure that 5% of the overall images in that group is grayscaled. So this particular collaborator has 95% color image and 5% grayscale. And in the second collaborator, we just turned it around such that 95% of the images are grayscale and so 5% is color. And in doing so, like we kind of simulate for the data heterogeneity, and doing so would even hopefully like help the model to be more robust and handle that kind of non-heterogeneity. And other simulation for testing this federated setup is class imbalance, where in addition to like non-uniform assignment across the different collaborators in terms of population, we also made sure that for each class, some collaborator doesn't have data for a particular class, and in doing so, the model will have this natural tendency to start catastrophically forgetting whatever it learned for those classes. And eventually, the model is more challenged to aggregate and learn when certain classes are missing in some collaborators. For the third case, which is the Shakespeare next character prediction data, this is text data from the Shakespeare play, and each role or actor in that play is kind of made one collaborator, and we just picked the top few actors from there and used it for the next character prediction model. So this is how we simulate for heterogeneity. And do our federated setup using that flow that I described earlier. So yeah, and how we split the data, this is based on divergence. So like I have the data from weight divergence presented for both the simulation types from CIFAR-10. For class imbalance, we see that when we look at the data on the left top, so across the different layers, if we compare the different iterations of the model, the divergence is very minimal for the initial layers. So layer on the x-axis, I have layer 1 till layer 9, and for layer 1 up to layer 5, we find that the divergences is like very small. After a point, it starts kind of exponentially growing and then coming down back again. So for this particular case where the divergence is very small for initial layers, we propose that like we split the data around layer 5, and I think from it also correlates well with the visual data that we saw earlier. Whereas on the class imbalance data at the right, we see that no such opportunities really exist. So the divergence is really high. So the conclusion is that while it can find opportunity for splitting a model at certain type of heterogeneity and certain data distribution, the methodology is not quite applicable across board. Though it's not applicable for accuracy, we do see that it comes with some network bandwidth reduction benefits. So from that context, even if the accuracy is still the same as FedAvg, it can bring in some benefits in terms of bandwidth, and hence desirable for different types of heterogeneities. So yeah, moving on to the results that we see with our divide and conquer model. So for CIFAR-10, we tried the different algorithms that we proposed, including FedAvg, FedProx, and FedMA. And for the color imbalance criteria, we simulated across two different types of color imbalance. 595 was a split I explained earlier. We also tried a couple more splits where 25% of the data was made grayscale. So like across board for color imbalance, we see that the divide and conquer algorithm that we have, despite being very simple, uh, gives like much better, significantly better accuracy results compared to FedAvg and FedProx algorithms, almost at par with FedMA and slightly beating it in some cases. Whereas for the class imbalance data set, we find a yeah, different kind of response. So we tried with the 5 and 10 collaborators. So for the vanilla divide and conquer, we see that the best it can do is more or less aligned with other set of algorithms. And this, though the accuracy levels is within the same range as the other algorithms, here there is some benefit in terms of bandwidth. Like only half the bandwidth will be used because we do divide and conquer. In one round, we only transfer weights for half the network, and it takes at least 2 rounds to do the complete weight transfer. But if we remove the constraint on the transfer and say that compare the different algorithms for the same amount of bandwidth, we find that this algorithm, the divide and conquer, kind of slightly marginally beats the other algorithms. And a similar result is observed in case of the Shakespeare dataset as well, wherein across the six collaborators that we tested, divide and conquer gets to the accuracy level which is similar to the other algorithms with half the bandwidth needed. So while we see that for the image color imbalance dataset, it can give significantly better accuracies. On some other type of heterogeneity, it does not do that, but still we get the benefit of the bandwidths for those kind of context. And this is especially beneficial if you have like if you do training across like thousands of collaborators, because as I show, explained in case of the Google keyboard example. So having bandwidth reduction is also an critical vector. So we get combination of both, or sometimes only one of the benefits. So yeah, I think that come to the end of the work. So like to summarize, DNC algorithm gives significant accuracy improvements for certain types of non-IIDness, though not everything, but still it can give network bandwidth benefits in the cases where it doesn't do a good job. But if we align the different algorithms that we compare in terms of the bandwidth, for most of the cases, DNC can perform better than the other algorithms that we picked. And it is based on FedAvg, which is the most common kind of algorithms deployed out there, and hence can be easily absorbed in any of the commercially available tools. With that, yeah, that ends my presentation, and I can take